Hey, this is Dr. Foot. I have today a quick tutorial introduction to a couple of my favorite packages for visualizing networks in R, tidygraph and Ggraph. These were both developed by Thomas Lynn Pedersen. I have a little bit of a ulterior motive here. I think they're great packages. I think that he has sort of moved on to other projects. They have not seen a lot of love, so I'm hoping to increase the profile of them a little bit so that people will continue to maintain them. I think they're just great. So the idea is, kind of assume that you're at least have a passing familiarity with iGraph, which is a great package for doing lots of network things in R. And in Python, they have a Python version as well. One of the weaknesses, I think, of iGraph is I think that the plotting is not great. The figures aren't great. So these two packages do two things. One is to make it easier to kind of manipulate iGraph or network objects, and the other is to introduce a lot of cool visualizations for them. And so one of the problems with iGraph, I think, is that it sort of has this kind of strange, kind of hidden structure for how networks are organized. So the tidygraph, which is the first package we'll talk a little bit about, extends the tidy paradigm, the idea of kind of data frames, tables, as a structure for representing data, flat files, flat tables as a structure for representing data, and extending that to networks. So what would a network look like? And it represents it as kind of two tables, a table of nodes and node attributes, and edges and edge attributes. And so let's see how that looks a little bit. First, we'll load the libraries. I kind of included this and included the warning messages as well, so that when you load it, it should look similar to this. So we're going to use iGraph. Both tidygraph and Ggraph use iGraph under the hood, and we'll use a few functions from it as well. Tidygraph, Ggraph, and tidyverse. If you don't have any of these, if you get an error that says you can't find this package, then you just need to run install that packages, and then put the package name in quotation marks. And then finally, these are sort of the packages I put at the top of all of my network graphing code. And the final one is set graph style. This is part of Ggraph, I believe, that just sets the style to a nice style for, it removes the gray background that's the default of ggplot, removes legends, I think, or axes, etc. So it's just a style that's more appropriate to graphs. And it'll set it throughout the whole, the rest of the code that follows. Okay, so the first thing I want to show you is how to get to the data. So the first thing, I assume that you know how to get your data, whatever it is, into an iGraph network object. If you don't know how to do that, there are tutorials. There's ways to figure that out. iGraph has a bunch of tools for doing that. So I'm assuming you know how to do that. Once you have an iGraph object, convert it to a tidygraph with as table graph. Like this. So let's say this creates a random network of 50 nodes where a 40% chance of each edge existing, and then we just convert it to a table graph or a tidygraph object. We can look at the tidygraph object by just typing the name of this variable g, and you'll see there are two data frames, two tables. The node data, which is 50 rows but 0 columns, so there's nothing in it right now. There are no attributes of these nodes. And then edge data, which will always include from edge and a to edge, and then the edge number. But you can also have other attributes of those, as we'll see in a minute. So one of the things that you might want to do, I'll show real quickly, and then actually at the end of the tutorial talk a little bit more about this, but is like mutating a table, doing some sort of operations on it. And so the key idea, these are tables, so we can do things, use sort of the tidyverse sort of set of tools, type of operations on them, which is much easier than the way we have to do things in iGraph. I think this is just a really powerful paradigm for manipulating graphs and visualizations of them. So, but we have to do like this tidygraph object has these two tables. First, we have to tell it which one we want. So that's what this activate nodes or activate edges says. I want to manipulate the nodes table or the edges table. So this one, quickly, this create notable just loads this Zachary karate data, and then we'll pipe it to activate the nodes, and mutate, which is mutate from dplyr, creates a new column called degree, which is equal to centrality degree. So degree centrality, which is just there are a bunch of centrality measures, and they're each centrality underscore, and then measure. We'll see another one in just a minute. And so now we have this new column called degree, which is the degree of each node. So how many edges each node has. This is not, note that I didn't say this, it's as a variable, so it's just output to the output, and then it disappears. But we can also do things like exporting these as tables once they, once we've got the table set, or once we manipulate it the way we want to, output it as a tibble, and then use something like ggplot. So this is, we'll take those Zachary data as well. This time we'll do edge between a centrality, change it into a tibble, and then send it to ggplot. So if you're familiar with ggplot, this is how you make a histogram in ggplot. I'll go over some of these concepts a little bit later for network diagrams, but this is, my intent is not to teach you ggplot today. So if it doesn't make sense to you, the ggplot's a really powerful plotting library for R, so you can learn about that. But basically, this is how you make a histogram, where our x-axis is equal to this betweenness BW variable that we created. So here it is. So that's a histogram of the edge betweenness for that Zachary karate data. So that's kind of the big idea of tidygraph, right? Is this idea that you have these, and we'll talk a little bit more about it at the end, but these two kind of data frames, tables, spreadsheets, however you want to think about it, and then you can manipulate those and then sort of save them back, visualize them, etc. We'll see that a lot more. Okay, so the next package is Ggraph. So Ggraph is a set of tools built on ggplot, based on ggplot. So you can, the idea is that you sort of add layers. So we take our network object, and then we add layers of visualization. So this is called the grammar of graphics. I encourage you to read more about it, but it sort of applies this idea for building network plots, which I think it's really cool. There's a lot of different geoms, it's called, for visualizing edges and nodes. I am going to focus on kind of the two simplest. I think they work well, they look nice. So geom node point, so this treats nodes as typically a circle, but as a point. It can have a shape, but it's basically a point. And geom edge fan, which treats edges as straight, typically, unless we'll see in a second, unless there are multiple edges between the same set of nodes, in which case it has two curved edges. So often we'll want to visualize something, change the color, the size. I guess those are the two main ones. Maybe the opacity of nodes, sometimes the shape of nodes and edges. And so the key idea, let's look at this plot first and see what it's doing. So there's a few things that it does. One, and then we'll look at the code, right? One is it changes the color of the edges to this blue, changes the color of the nodes based on the group, right? So there's a legend over here. Group 1 are the red ones, group 2 are green, group 3 are blue. So then let's see what's going on here. So we load the Zachary data, activate the nodes. We create a group variable. This is based on a grouping algorithm. Again, kind of beyond the scope of this tutorial. You can look about grouping, but it's sort of an inferred grouping. And then this is the key idea, is like we send this, instead of to ggplot like we did above, we're saying that this is going to be a Ggraph. We add geom edge fan, so this is the edges, and then we have width equals 0.2, so we change the width from the default, and color equals light blue. Note For the edges, this applies to all edges. They're all width 0.2, and the color for all of them is light blue. On the other hand, when it comes to the nodes, we put them within an aesthetic mapping. So this says instead of applying something universally, map an attribute or an aesthetic of the plot to something in the data. So in this case, we're mapping color to the group variable, right? So we created that group variable, put it into the nodes, and now we are mapping the color of the nodes to that group variable. Yeah, the rest is kind of, you don't need to worry too much about it. Those are the key ideas. So that's the kind of the key concept, which we'll see again, is this idea of universal things go outside of the aesthetic mapping, and things we want to map to the data go inside this AES. And that's the first argument to these geoms. So we often want to color instead of by group, which was inferred, which we showed. I'm going to go to this data set about Dutch school data collected. I don't remember when, but by Andre Connect. So this downloads it. This shows how you can create if you have nodes and edges CSV files. You create it with graph from data frame, and then we'll change it again. That changes to an iGraph network object, and then this changes it to again a tidygraph object. So here's what it looks like. We've got delinquency and alcohol use and sex and age and ethnicity and religion for the nodes, and then for the edges we have from, to, and a type, which is either friendship or primary school, that they went to the same primary school. Okay, so if we want to, let's take this data and say we want to visualize this alcohol use variable. So we'll take our edges. This time we'll make them 0.5, change the color to gray for all of them. So again, it's universal, and then map again the aesthetic mapping color to alcohol use. We can also, we can include it doesn't have to be all or nothing, either all mapped to variables or all universal. We can include universal things afterwards. So inside of this aesthetic mapping, color equals alcohol use. Outside, size is equal to 3. So all the nodes are equal to size 3. And then this is, we'll talk a bit more about colors, but this is adding this neat color scale. So one thing that's interesting about this, we can notice that there is as many as 4 edges between nodes. It's actually a directed graph with 2 different types of relationships. So we can also, let's take the edges, and now we'll do a mapping from color to the type of the edge. So we have now friendship and primary school as our 2 edges. So these all went to the same primary school. This group went to the same primary school. And then the red are the current friendships. Talk just real quick. This is an example of how to do your own colors. So alcohol use, it has the color is here, and then we just use this scale, the Viridis color scale. If we want to do manual colors, scale edge color means I want to change the edge colors manually, and then you create a what do they call it? A named vector, where you give the name of each. So friendship, if the variable is equal to friendship, then use this color. If the variable is equal to primary school, use this color. And you can either use hex notation, or there are a whole bunch of different names that are possible. Okay. We may also want to change the size of the nodes or the width of the edges. So this is quickly how you do that. So here we'll maintain the same colors for the edges, but let's say we want to change the size of the nodes based on delinquency. So size equals delinquency. This will change. Notice how some are quite small, some are quite large. This is based on this delinquency measure. And similarly for edges, we could have changed this so that instead of by color, maybe they were different widths. I think that's probably a bad visualization, but you could do it. Usually, width would represent something like edge weight, So edges may have may measure something like how often people interact, right? And you'd want thicker ones for people to interact more often. So that's pretty common. So instead of, we use size for nodes, width for edges. So it would be just right here, color equals type, comma, width equals weight, for example, instead of this width equals 0.5. So that's colors, sizes, etc. The other big concept is layouts. I have shown, and I will continue to show, basically kind of sociometric layouts. These are, where nodes equal edges, or nodes are dots and edges are lines. But there are a bunch. I think one of the cool things about Ggraph is that there are cool other options, dendrograms and tree maps and other cool things, which I think are they're typically less useful when nodes represent people, as they usually do in my data and the things I'm interested in. But there are some cool uses, right, for those sorts of things. But I'm focused on more kind of traditional layouts. So this is, we've seen this a few times before. I kind of have skipped over it. But in these, layout equals stress, I've skipped over that. It says, what is the algorithm that determines where the nodes and edges are laid out and how they are laid out with each other? Many of these, stress and this KK algorithm, are both, I believe, spring embedded, which means that nodes are in general repulse each other. They're kind of physics based. They repulse each other unless there's an edge between them. So it's sort of like a spring that's pulling them together, but they're typically repulsed, and therefore things that are closely connected and especially connected in multiple ways, group together. So it's a nice way of grouping things in an intuitive way. So this is the same. So notice how this. Oops. Let's go back. Sorry, to the Zachary data. Here's how it looks with the default stress layout, and here's how it looks with the KK algorithm. So you still see sort of the same two main groups, just they look a little bit different. Other layouts can show, well, it can really change how we interpret and how we see things. So here's a circle layout, which I think does a really nice job of showing where the kind of less connected people are, but it's often confusing, right? This node actually has quite a few connections, but out here in the periphery, it's hard to tell that there are two groups. In general, not as nice, and I think that usually what we care about are seeing groups and things like that, and so some of these other types of networks layouts are nicer. There are some cool. This is really just to show off that it took me a while to figure this out. I think it's really cool looking, but you can do really cool things. So this is the focus layout. I honestly found an example. There's a link there. It's really complicated. I don't really understand a lot of it now that it's been months since I actually did it. I copied and pasted and adjusted things until it looked how I wanted, and so. But the idea is what it's doing, which I think is really cool. It's an ego network, which is centered around one node. So this is node 3, and then here the nodes are all distance 1 from node 3, and distance 2, and distance 3. So we've colored each of them by how far they are. We have put them in these concentric circles. It's really cool, and yet they're still also closer together if they're connected to each other. I think it's neat, but again, definitely not a kind of typical thing that you would do. Not a typical layout, but it sort of shows the power if you really want to dig into it, that you can manipulate Ggraph in ways that do this. Okay, so I talk a little bit about some advanced concepts. One is directed edges. One thing I don't like about Ggraph is that it's not great for drawing arrows. It's kind of a pain. You can see, look at all this code just to draw arrows. I think iGraph does a much better job with that. And so I think the better approach, especially, so this actually really fails if you're changing, for example, if these nodes change size based on some attribute. then even this code doesn't work. You have to really do some kind of crazy things to get it to work. I think the better way is by just adjusting the alpha of the edges. So this is how transparent an edge is. And so it's sort of actually built in pretty nicely. So this geom_edge fan, you just do alpha equals stat index. You don't really need to worry about the meaning or why that works. And then you add a legend. So this last line adds the legend, and it shows it, right? The from node starts light, and it's going to the dark node. So this edge, for example, is going from this node to this node, right? Because it starts light and goes dark. I think it's pretty intuitive. It takes a minute. It's not quite as nice as an arrow, in the sense that we don't have this intuitive sense of direction with it. But once you read these for a second, I think it's quite pretty looking, and you can figure it out pretty quick. Okay, another idea is facets. I love this. I love this aspect of Ggraph. I think it's very difficult to do something like this in iGraph, and so this, for example, shows. So what this is our everything else is exactly the same. All this code is just what we've done before. Color equals alcohol use, size equals delinquency, scale color viridis. We've got our edges. So all we add is this code that's facet nodes, and then this tilde is by sex. So we have the female and male nodes, and so it basically creates two new networks. Like what's the friendship and primary school network of just females and that of males? I think it's really slick and really easy to do. Another thing we may want to do, especially with this network, right? Especially when we have two different types of edges, is do the same thing but by edges. So this again copies and pastes all that same code, and then we just facet the edges by type. So here's the friendship network. Here is the primary school network. The neat thing about it is that it'll keep all of the nodes in the same location, so you can kind of quickly compare across them. So obviously, when you have different nodes, it won't keep them in the same location. But when you have different edge or the same nodes in just different edges, it'll this node is the same as that node, right? These two purple nodes are the same, etc. Finally, you can also do it in both directions. And so this one's a little bit silly, but this is ethnicity by sex. You can. There is a way to do it by edges and nodes. I don't remember how, but so this is just females with ethnicity 1. I don't remember what the ethnicity stands for. One of them is Dutch. I think it's Dutch and non-Dutch. So this is males with ethnicity 1, females with ethnicity 2. There are only a couple of folks, and people where there's no ethnicity. There's one female. So that's, in this case, not a useful plot, but you can see how that would be useful. I'm going to talk a little bit more about table manipulations. We talked about mutate, just because we had to use it for so many things. But you also may want to filter, right? So instead of faceting, we may want to just filter to only the friendships. So this is just that friendship network. When we get rid of the non-friendship. So we activate the edges and then filter where type equals friendship. So that's filter, and then we visualize it the same. And again, I think that's one of the really powerful things about this kind of grammar of graphics is that you can do things like change out this kind of pre-code to prep your data in a new way, and then you just keep all the same visualizations and it visualizes it really nicely. I think it's slick. Mutate, we've talked about mutate already, but here's another example that we can actually do two things together, right? So we activate the edges, filter to friendship, and then activate the nodes and mutate where coreness equals node coreness. I think that's a great measure sort of how inside of a network someone is. They have a lot of friends that also have a lot of friends. And then we're change the color to be based on this coreness. So these all have a coreness of 7, and then as you get out toward the periphery, the coreness goes lower. So we can mix and match again. So this is filters to friendship just where it's mutual, and then we add the coreness. So this is again just the coreness for mutual relationships only, right? So we have this whole new set of edges, just the mutual friendships. And then one other visualization I really like is to color the edges based on similarity or homophily. We want to show whether people have similar drinking behavior to their friends. So let's take the same data, activate the edges. It's kind of a little complicated. I give a description in the text here, but let's just go through each line, activate the edges, filter where the type equals friendship, and then here's the kind of the key. So we're going to create this new variable called drinking diff, which is equal to the absolute value. That's what this is. And then this .n lets us get to the other data frame, the nodes data frame. So the nodes data frames, right? Because we're in edges. We've activated edges. We want to manipulate. We want to create a variable about an edge. But we've already activated edges and not nodes. And so we can't. So the only way to get to the nodes is with this .n. And then the parentheses. So from the nodes, get the alcohol use of the from node. So so for each edge, it has a from and a to. So we're going to take the alcohol use of the from node and subtract the alcohol use of the to node. In other words, we're getting the difference from these two nodes for each edge. So for each edge, find the difference of drinking behavior between the two nodes and take the absolute value of it. So how different is it? That's what this drinking diff is. All the rest is the same, except now the edges, the color is going to be this drinking diff. And the nodes, we're going to color them by alcohol use. Okay, so we can see the drinking difference. The more, the lighter color, the yellow, there's a big difference between the nodes, and alcohol use, the higher or the lighter, the more alcohol use. So for example, these yellow ones in the middle, this person in the center has high alcohol use, but these yellow ones have friends who do not have high alcohol use, right? So that's the idea there. We can see that there is, some like kind of a one-ish is kind of pretty typical for the difference between them. There is quite a bit of purple where there's no difference. But I think I think that's neat. The gray, just as a note, the gray here means that this data is missing for at least one of these nodes. Well, you can see who it's missing for because they are gray, right? So if we don't know their drinking behavior, then we can't evaluate the difference between them. So it just colors them gray. So that's the idea. I think it's a really cool visualization. Okay, a few other kind of tips and tricks I'm going to quickly go over. If you've made it this far, well done. One is that you don't have to. I sort of built every visualization starting with a network object. You don't have to do that. You can create a plot and then add to it. And so this creates one. Oh, one other thing that's worth mentioning is the difference between pipes and plus. For historical reasons, they kind of do similar things, but you use pipes as you're manipulating things. So every line before you get to Ggraph is pipes, and then once you get to Ggraph, everything after that is plus. So I think of it, you can think of pipe as like, okay, take the input of this and send it, or the output of this first operation, send it as the input of the next one. Output of that one is the input of the next one. And so you sort of send it through these pipes, and then you send it to Ggraph, sorry. And once it's there, it's a graph, and we're adding layers. So the plus is like adding. That's mostly a mnemonic, but that's a good way to think about it. You're adding layer, add a layer, add a layer. And so yeah, so that's what we'll do. So that's how it works. So this saves plot as P, and then I type P at the end to visualize it. So here's our plot. It has just friendship ties, the layout is stress, and we have gray edges. So there we are. That's our basic thing. We don't even have nodes. And then we can say plus. We'll just take our P and say plus GM node point, scale color radius. So we could have done this earlier, right? If we know that usually we want to be visualizing the friendship nodes or the friendship edges with color gray, then let's just save that in the beginning. We don't have to re-copy and paste it into every piece of code we write. We can just add the things we want to change. Maybe we'll visualize alcohol use, and then we'll visualize, I don't know, what are some of the other things? Visualize delinquency, and we'll change the color for each of those, and we'll have sort of these series of plots. And so it makes sense to just change the things that you need to change. We can also, another approach is to save a filtered or mutated version of a network. We might save as friend G, that's just filtered to friendship. And then we don't have to keep filtering it every time. Sometimes this is really valuable if you have a really big network. Let's say, you have a network with thousands of edges, and instead of doing this work of filtering every time only the edges you want, if you're always going to filter them, save that as a new network. Save it as a new network, and then just work with that one. One other kind of trick is that it's the layers are in order, right? And so the last things go on top of the graph, or of the plot. It's a good way to think about it. And so if you draw the edges last, so this draws the nodes first and the edges last, it looks bad because the edges go on top of the nodes. So this is the exact same plot, but with the edges drawn first and the nodes drawn afterward. Good. One other thing, changing legends and title. So this is, again, kind of advanced, but I think it's worth it for making things readable. So we can use this whenever we're using a color scale that also creates a legend, and we can give a name to it. So this is where that alcohol use name comes from. When we're here's the manual color scale. Here's where edge type comes from right here. The size scale, we can give that a name, delinquency, there it is there. And we can give, with the labs function, a title, the relationship between delinquency and alcohol use. Let's see, is this the last thing? Oh, almost there. So a few more things. One is dealing with missing values. So NA is missing data. So for example, we don't have delinquency and alcohol use data for some people. We talked about how that's gray. Oops, not in that one. This one for alcohol use. That's one way to deal with it. I mean, Ggraph deals with it okay in some cases. Resizing does not work as well, right? So note, if we change size based on alcohol use, it just removes those nodes. And you'll note in the plot, it appears there's edges, for example, right here, but no node there. There's not a great way to fix this problem. I mean, it's missing data. If we're going to visualize something that's missing, it's just not. It's not possible, right? Like, what size should it be? We don't know. So one thing you can do, there are a few options. One is to leave it as it is, which is okay. Another is to filter it out. If you have a good reason to do that, we can just remove those nodes, right? So note, this is a different plot. These are different. I mean, it's the same set of nodes, but now missing those. So that's what this filter to only those. So is in a alcohol use. So this exclamation means not. So it's not missing. So filter to only those where alcohol use is not missing, and then size by alcohol use. So that's one option. We could replace NA. So that's what this is. Instead, we mutate where alcohol use equals replace NA. So it'll only change the ones where it's missing with a 1. So now all the missing ones are a size 1. It's the kind of the closest we could do. We could have done 0.5 as well, or we could have done the median, or we could have done something more complicated to impute the missing data. But yep, those are sort of the main options. Okay, I think this is the last thing. Finally, we might want to we can save the original position of nodes. We might want to keep them in the same place and then show it again. So you can create a layout. So L equals create layout, and then you can, it's a little bit complicated, and then select X and Y. So that's the X and Y location. You can think of it as a Cartesian plane, X and Y location of each node, and save it as a matrix. And then, so that's our layout, and then we tell Ggraph that the layout equals L, right? So we save that as L. And then, so instead of layout equals stress or layout equals KK, we say layout equals L, and it will give us the same exact, put the nodes in the same place. So yeah, so maybe we filtered only to friendship. We want to compare these two. If we had just run it with layout stress, it would have put all the nodes in different places, right? It will restructure them based on now the friendship edges. But in this case, it keeps them all in the same place. We can, maybe that helps us to see, right? Like, oh, there's a whole bunch of edges missing right here, or these ones right here missing, right? It makes some things more visible because the nodes are all in the same place. Yeah, there's another, if you're filtering out nodes, there's an example here, but I think that's plenty for today. Hopefully that's helpful. I hope that you'll take a look. I think this is a super, super cool set of packages. All of this code will be available as HTML file, as an R Markdown file, and I'll put that in the notes. All right, thanks.